April 1st, 2026. Kennedy Space Center, Florida. The Space Launch System stands on Pad 39B. 322 feet of rocket and spacecraft balanced above a launch tower that once held Saturn fursives. At 6:35 p.m. Eastern Time, 4 astronauts ignite 8.8 million pounds of thrust and ride Artemis 2 into history. The first crewed mission beyond low Earth orbit since Apollo 17 in 1972. Cameras track the ascent from the ground, from recovery ships, from the Orion spacecraft itself. One airborne camera platform circles at approximately 45,000 feet, flying at 350 miles per hour, carrying high-definition imaging equipment designed to capture every second of the SLS stack's climb through the atmosphere. The aircraft carrying those cameras is a design that originated in 1944. 82 years separate the drawing board from this flight. There are exactly 3 of them left. In the aviation community, in research papers, in Smithsonian Magazine, in the words of the crews who fly them, they are called the long wings. The distance between 1944 and 2026 spans the entire jet age. It contains the birth of supersonic flight, the introduction of intercontinental ballistic missiles, the moon landings, the space shuttle program's complete arc from first flight to final mission to museum display. The Lockheed P-38, the de Havilland Mosquito, the B-17 Flying Fortress, all gone from operational service by the 1950s. Museum pieces for 60 years. The aircraft watching Artemis 2 launch was designed in the same year those aircraft were flying combat missions over occupied Europe and the Pacific. The question this raises isn't incidental. It's the central puzzle of one of aviation's least examined stories. What did the engineers who drew those original lines in Lancashire, England, get so fundamentally right that the world's most advanced space agency, 82 years later, still hasn't found anything better for certain specific jobs? The answer begins not with NASA and not with the Cold War, but with a chief designer named William Edward Willoughby Petter, and a requirement that in 1944 seemed to most people in British aviation like an impossibly ambitious brief. In 1944, the English Electric Company received an invitation from the Air Ministry to participate in discussions about a new jet-powered bomber. The timing was odd. English Electric had spent the war years manufacturing other people's aircraft, Handley Page Hamptons, Handley Page Halifaxes, producing thousands of them under license without developing any meaningful internal design capability. The company's chairman, Sir George Nelson, recognised both the opportunity and the problem. Here was a chance to become a genuine aircraft manufacturer, but English Electric had no design team capable of doing it. The man Nelson recruited was W.E.W. Teddy Petter, who left Westland Aircraft in March 1944 and joined English Electric as chief designer. Petter came with credentials. At Westland, he had designed the Lysander, the high-wing monoplane that became the RAF's primary army cooperation aircraft. But the Lysander was a slow, deliberate machine built for short-field operations. Nothing in it anticipated what Petter was about to attempt at English Electric. When he arrived, he brought with him a design study for a twin-engine aircraft he had been developing, something the Air Ministry had found interesting as a bomber concept. English Electric gave him a small team and told him to develop it. The formal requirement Petter was working toward had originated inside the Air Ministry in 1944. A successor to the de Havilland Mosquito, the twin-engine fast bomber that had proven almost impossible to intercept in service. The Mosquito's philosophy was speed and altitude as defense. No gun turrets, just performance. The new aircraft would take that principle further. It would be jet-powered. It would fly faster and higher than the Mosquito. And it would carry no defensive armament at all. That last point deserves careful examination because it defined everything that followed. The Air Ministry's logic, stated explicitly in the design philosophy that shaped Specification B.3/45, was straightforward. If an aircraft can fly high enough and fast enough, interceptors can't reach it. Defensive armament, gun turrets, ammunition feeds, gunners' positions, their associated structure, added weight, added drag, and added complexity that was antithetical to speed and altitude. Strip it all out. Build the most aerodynamically clean aircraft that 1940s engineering could produce, and trust the performance envelope to keep the aircraft alive. Petter had internalized this logic completely. By mid-1944, he had conceived the basic architecture. The Ministry of Supply formally issued Specification B.3/45 on January 7, 1946, which codified the key requirements. Twin Rolls-Royce Avon turbojet engines, not the Griffon, not the Merlin, which were Rolls-Royce piston engines from an entirely different technology family, but the new axial flow Avon, still under development, promising around 6,500 pounds of thrust per unit. A crew of 2 with ejector seats. Performance targets set at 440 knots at 40,000 feet. A service ceiling of 50,000 feet. And a range of 1,400 miles. Petter considered swept wings. German aerodynamicists and, gradually, American designers were moving towards swept planforms for high-speed aircraft. Petter rejected the configuration. At the subsonic cruise speeds he was designing for, not Mach 1 but high-altitude cruise, the structural and aerodynamic complexity of a swept wing didn't justify its performance at those speeds. He chose a mid-mounted straight wing with engines buried in nacelles within the wing structure, close to the fuselage. The engines remained accessible for maintenance. The wing provided efficient lift at altitude. The configuration kept the center of gravity manageable with different payload configurations. The wing itself was a piece of engineering that contemporary aeronautical engineers found impressive. A leading edge formed from a single sheet of light alloy, wrapped around to 40% of cord, bonded to redux-bonded stiffeners through which the ribs passed, secured by adjustable eye bolts. No external joints or fastenings from the leading edge to the main spar. The result was a wing profile of unusual aerodynamic precision, the kind of surface finish that reduces drag at altitude in measurable, sustained ways. The design drew comparisons to the Mosquito's wooden construction philosophy. Not a single component wasted. Everything oriented toward the aircraft's core performance requirement. Assemblies for the first prototype, serial VN799, arrived at Warton Aerodrome in Lancashire in early 1949. On May 13, 1949, a Friday, English Electric's chief test pilot, Wing Commander Roland B. Beaumont, lifted VN799 off the Warton runway for a 30-minute first flight. Beaumont noted rudder overbalance as the only significant handling characteristic of concern. Otherwise, the aircraft flew. The handling responses were closer to a fighter than a bomber, surprisingly light and responsive. The project had found considerable government support in the late 1940s. In March 1949, in advance of VN 799's first flight, English Electric had already received an instruction to proceed with production. By the time Bement landed after that first 30 minutes, the Air Ministry had placed orders for 132 aircraft. VN 799 appeared at the Farnborough Air Show in September 1949 and caused a sensation. In January 1950, Sir George Nelson gave the aircraft its name, Canberra, after the Australian capital, because Australia had become the aircraft's first export customer. On April 23, 1950, the first production standard B-2 VX-165 flew with Avon RA-3 engines, producing 6,500 pounds of thrust each. In May 1951, the Canberra B-2 entered RAF squadron service with number 101 Squadron, the service's first jet-powered bomber. What Petter had built was, in the bluntest technical assessment, an aircraft optimized for a single thing: being difficult to reach. Everything else was secondary to altitude and the aerodynamic cleanliness that enabled it. The Canberra proved this emphatically in its first decade of service. Throughout most of the 1950s, the Canberra was the highest-flying operational aircraft in the Western inventory. Standard service ceiling for the B-2 was 48,000 feet. In the reconnaissance variants, equipped with progressively more powerful marks of the Avon, the RA-7 in the PR-7, the far more powerful RA-24 in the final PR-9, the ceiling climbed further. In 1957, a specially prepared Canberra established a world altitude record of 70,310 feet, demonstrating what the basic airframe philosophy could achieve when pushed to its limit. Contemporary jet fighters couldn't touch it. The type was exported to 15 countries, earning over £90 million in export contracts, serving air forces from Argentina to Pakistan to South Africa to India. The Glenn L. Martin Company received a USAF license to build it as the B-57 after the Air Force found that no American aircraft could match what the Canberra already offered. Martin's American B-57 entered USAF service in mid-1953, powered by the Wright J-65, an American-built license version of the Armstrong Siddeley Sapphire, a different engine from the British Avon, but occupying the same nacelle positions in the same airframe architecture. The B-57's first variant was essentially identical to the original English Electric aircraft. What Petter had drawn in 1944 was flying over American airfields in 1953. The aircraft's altitude dominance created its own mythology in the early Cold War. During the 1950s, NATO air defences considered the Canberra effectively immune to interception above certain altitudes, because contemporary interceptors, the Hawker Hunter, the North American F-86, ran out of performance before they could reach it. RAF crews flying Canberras at 40,000 feet and above described a world where they operated essentially alone, photographing whatever they needed to photograph, confident that nothing below them could catch them on the way home. Number 39 Squadron and Number 58 Squadron operated Canberra PR variants on Cold War reconnaissance missions from bases including RAF Lucca in Malta, taking long-range photographs over denied territory at the edge of the stratosphere. Then came the U-2. Lockheed's intelligence platform, introduced operationally in 1956, was designed for altitudes above 70,000 feet, more than 20,000 feet above the Canberra's standard ceiling. The CIA's thinking was explicit. An aircraft operating that high was beyond the reach of Soviet interceptors, and the photographs it could take of Soviet territory would be unlike anything previously available. Wikipedia's entry on the U-2 program captures the moment precisely. At the time the U-2 was introduced, the highest flying aircraft available to the US and its allies was the English Electric Canberra, which could reach 48,000 feet. The U-2 had been built specifically because the Canberra's ceiling wasn't high enough. A story circulates in RAF aviation culture from that period, never officially documented, but repeated by former RAF personnel in forums and oral histories. A former RAF officer with 28 years of service described hearing it. The only story he heard in a similar vein was that a Canberra took a photo of a U-2 from above. The fuller version, as RAF crews tell it, involves a U-2 crew betting they could conduct a reconnaissance pass over England without being photographed, confident in their altitude advantage, and a Canberra PR variant, operating near its certified ceiling, catching them from comparable or superior altitude. The photos in the story were presented at a beer call. No date, no unit, no named crew members. The story's aerodynamic plausibility depends on the Canberra PR9's classified service ceiling, which official sources describe only as well above 48,000 feet, with contemporary assessments describing the PR9 as similar in role and performance to the U-2. Whether the story is literally true is unknown. What it reflects is real. The Canberra's altitude performance was so unexpected, so disproportionate to what an aircraft from 1944 was supposed to be capable of by the late 1950s, that RAF crews built cultural mythology around it. The aircraft kept pace with machines designed specifically to supersede it. Among the crews who flew both types, that discrepancy was worth a story. The U-2's arrival didn't retire the Canberra. It changed how the aircraft was used. The pure altitude gap pushed Canberras towards specialised roles: atmospheric research, weather reconnaissance, photographic and electronic intelligence in lower threat environments, where the combination of ceiling, payload capacity and range kept them relevant. But the retirement wave was already building from other directions. Supersonic interceptors made even the Canberra's altitude ceiling a less reliable defence. Ballistic missiles made strategic bombing by aircraft increasingly obsolete. And specialised reconnaissance satellites were beginning to do from space what the PR variants had been doing from the stratosphere. RAF Bomber Command retired its last Canberras on September 11, 1961. The Germany, Cyprus and Singapore-based squadrons continued for years after, but the core bomber role was done. The US AF B-57 combat variants wound down through the Vietnam era. Australia, which had built 48 Canberras domestically at the government aircraft factories and flown them in Vietnam, retired its last in 1970. The Argentinian, Pakistani and South African operators followed in subsequent decades. The Royal Air Force held on with the PR.9 reconnaissance variant until June 23, 2006, when the RAF retired its final 3 Canberras in a ceremony at RAF Marham. 55 years of service, 57 years from the first flight. The final variant in RAF service was the PR-9, the photographic reconnaissance model, with the RA-24 Avon engines and redesigned inner wing section that had given it performance comparable to the U-2. India, which had inducted the Canberra in 1957, held on the longest of any conventional military operator. On May 11, 2007, the Indian Air Force issued a press release marking the phasing out of its Canberra aircraft after 50 years of its glorious service. Every nation that ever flew the Canberra eventually retired it. The logic was sound. The Cold War had ended. Satellites had replaced strategic reconnaissance. More capable attack aircraft had arrived. Better trainers existed. The aircraft's time had passed. Its 1944 design philosophy, brilliant in its era, belonged in a museum alongside the Mosquito and the Halifax. 3 aircraft in Houston had not received that particular message. To understand why those 3 aircraft still exist, the story needs to go back to 1962 and a specific crisis in American intelligence collection. A signals intelligence operation conducted from Peshawar, Pakistan, had ended abruptly when the Pakistani government evicted the Navy for committing too many violations of restricted airspace. Communist China was preparing its first nuclear test, expected in October 1964. The Air Force needed a platform capable of operating above 60,000 feet, carrying substantial sensor payloads and doing both simultaneously. Capabilities that the RB-57D, an earlier extended-wing Canberra variant, had promised before stress fractures in wing spars grounded the fleet. General Dynamics, through its Fort Worth division, received a sole source contract to develop what became the RB-57F under the program called Pee-wee-3. The engineering team took the basic B-57 fuselage, Petter's airframe in its American incarnation, and rebuilt it so completely around new requirements that the result was described internally as virtually a new aircraft. New fiscal year 1963 serial numbers were assigned to all 21 converted aircraft to reflect how extensively they had been remanufactured. The wing was the most dramatic change. The original B-57B had a wingspan of approximately 64 feet. The new wing measured 122 feet 5 inches, nearly twice the span. It was a computer-designed structure, unprecedented in its analytical approach for the early 1960s. Using aluminium honeycomb panels that bonded outer and inner aluminium skins to a honeycomb of aluminium and fiberglass. All control surface gaps were tightly sealed to reduce drag. Wing flaps were eliminated entirely. At the altitudes this aircraft was designed to reach, flaps were unnecessary, and the aerodynamic penalties outweighed any landing benefit. The vertical stabilizer was redesigned to nearly twice the area of the standard B-57B. Its height increased to 19 feet, improving longitudinal and asymmetric control at extreme altitudes. The Wright J-65 turbojets were gone. The RB-57F received Pratt & Whitney TF-33 P11 turbofan engines, each producing 16,000 pounds of thrust, more than double the original power plants. Production aircraft subsequently received the upgraded TF-33-P-11A, delivering 16,500 pounds of thrust. For additional sealing, 2 Pratt & Whitney J60-P-9 turbojets in pods outboard of the main engines could be air-started at altitude, each generating approximately 3,300 pounds of additional thrust above 40,000 feet, adding 2,000 to 3,000 feet to the aircraft's maximum altitude. The nose was lengthened to accommodate navigation equipment. The cockpit was modified, and sophisticated sensors were integrated throughout. 21 aircraft were converted between 1963 and 1967, remanufactured from existing B-57 airframes, RB-57As, B-57Bs, RB-57Bs, and RB-57Ds drawn from storage. The first prototype flew on June 23, 1963 at Edwards Air Force Base. The results exceeded projections. The new wing generated so much lift that the aircraft was airborne after a takeoff roll of only 2,600 feet at sea level. It reached 50,000 feet in 18 minutes, climbing at 2,725 feet per minute. The RB-57D, assigned as a chase plane, couldn't keep pace. Over the following months, prototype aircraft flew operational evaluation missions along the German border at over 60,000 feet, taking long-range photographs into East Germany. The aircraft worked. High-altitude flight in the RB-57F required crew preparation comparable to U-2 and SR-71 operations. David Clark Company, full pressure suits, pre-breathing protocols, and the kind of pre-flight ritual associated with operations at the edge of survivable atmosphere. A pilot who flew the type in the Cold War era described the actual performance envelope with characteristic precision. The aircraft's max altitude is about 70,000 feet, with most missions flown at a pre-planned altitude, usually 55 to 65,000. In 1968, the Air Weather Service redesignated the fleet WB-57F, the W prefix indicating the Weather Reconnaissance Mission, though the aircraft's operational history encompassed nuclear debris sampling, strategic signals intelligence, and atmospheric research simultaneously. The WB-57F wings, when the aircraft sits on the ground without the aerodynamic loads of flight, droop visibly. The structure is built so lightly, every gram saved in service of altitude, that gravity pulls the wingtips downward when the aircraft is parked. At 122 feet span, the tips hang noticeably below the engine nacelles. It's the most immediately recognizable feature of the aircraft on the ramp, and one that reveals the engineering logic of the design with unusual directness. This machine was built to fly, and its structural choices make that priority visible, even when it isn't. The Air Force retired its WB-57Fs between 1972 and 1974, sending most to storage at Davis-Monthan Air Force Base in Tucson, the Boneyard. Before military retirements began, NASA had taken transfer of one WB-57F in 1972. Others followed as the military fleet shrank. 4 NASA WB-57Fs operated from Ellington Field, adjacent to Johnson Space Center in Houston. Then the fleet contracted further through the 1980s and 1990s. By the time the RAF was retiring its final Canberras in 2006, NASA's fleet had reduced to 3 aircraft: N926NA, N927NA, and N928NA. Air Force serial numbers 63-13503, 63-13295, and 63-13298, originally assigned the Cold War code names Rivet Slice 2, Rivet Chip 8, and Rivet Chip 11. N927NA, Rivet Chip 8, has the most extraordinary individual history of the 3. Its original identity was as a Martin B-57B, USAF serial 53-3918, before being remanufactured as an RB-57F by General Dynamics. After the Air Force retired it in June 1972, it went to Davis-Monthan. It stayed there for 41 years. The Berlin Wall fell while it sat in the Arizona desert. The Soviet Union dissolved. The Space Shuttle flew 135 missions. 3 different Cold Wars ended or transformed. N927NA remained in the Boneyard, wings drooping, untouched. In 2011, Sierra Nevada Corporation began a full restoration at Centennial Airport, working from airframe components that had been preserved by the Arizona climate. In August 2013, N927NA flew again, described by one account as the longest storage period for any military aircraft before returning to operational service. An online observer, viewing the 2013 restoration article, noted simply, "I even have a WB-57 Longwing." The nickname was already established. Smithsonian Air and Space magazine identified the WB-57F's expanded wingspan as the source of the aircraft's widely used nickname, the Longwing. The term appears in an Osprey military history of B-57 variants, in an academic paper from Embry-Riddle Aeronautical University, in a Springer academic chapter titled The Long-Wing Stratonauts. It isn't an official NASA designation. NASA's own Airborne Science Program pages list the aircraft simply as WB-57JSC. But it's the term that operators, researchers, and crews use when they're talking about the aircraft among people who know what they're talking about. At Ellington Field Joint Reserve Base, 9,000 feet of runway and a dedicated hangar support the WB-57 High Altitude Research Program, managed by NASA's Johnson Space Center. The operational ceiling of the three aircraft exceeds 60,000 feet, with pilots describing actual maximums around 65,000 to 70,000 feet, depending on payload configuration and atmospheric conditions. Endurance reaches 6.5 to 7 hours. Range extends to approximately 2,500 miles. Payload capacity is 8,800 pounds, distributed across belly bays, the nose, wing pods, and wing hatches. That payload number is the critical figure, the one that explains why the aircraft persists while aircraft with higher certified ceilings don't replace it. NASA also operates the ER-2, the civil derivative of the U-2, from Ames Research Center in California. The ER-2 flies at classified altitudes that substantially exceed the WB-57F's published ceiling. For pure altitude, the U-2's descendant unambiguously wins. But 8,800 pounds of scientific instrumentation is a different mission requirement entirely. The WB-57F can carry sensor suites that the ER-2's more limited payload envelope can't accommodate. For missions requiring both extreme altitude and substantial scientific payload simultaneously, missions that define much of what NASA's Airborne Science Program does, the combination available on the WB-57F doesn't exist in any other government platform. The instruments the aircraft carries document its range of missions with unusual breadth. For atmospheric science, advanced microwave moisture sounder sensors operating at 183 GHz for water vapor measurements, carbon monoxide and carbon dioxide measurement systems, single particle mass spectrometers for aerosol analysis, gaseous sampling systems for trace gas measurements. For Earth observation, APQ-102A side-looking radar for terrain mapping, high-resolution optical systems. For spacecraft support, the WB-57 Ascent Video Experiment, WAVE, a high-definition nose-mounted camera system originally developed for space shuttle monitoring, providing launch imagery from above cloud cover that ground cameras can't match. General Dynamics, during the original 1960s conversion program, had designed aerodynamically faired plug-in pallets for sensor integration, modular installation bays that let the aircraft's scientific configuration change with each mission, without major structural modification. The adaptability was engineered in, decades before NASA began using it. The WAVE system has documented every major rocket launch the WB-57F has supported. It provided detailed footage of space shuttle launches. It was deployed for Artemis 1 on November 16, 2022, capturing the SLS rocket's first flight. The system tracks not just the rocket's visible ascent, but the dynamics of engine plumes, structural performance of the vehicle during the acoustically and thermally demanding first minutes of flight. Data that engineers at Marshall Space Flight Center analyze for months after each launch. The aircraft has also flown through the exhaust plumes of Delta II rockets to measure combustion chemistry directly. Deployed to Afghanistan, fitted as an airborne communications testbed known as the Battlefield Airborne Communications Node, and was sent to Kennedy Space Center for video support of SpaceX's launch abort test for the Crew Dragon system. In 2013, WB-57Fs operating from Ellington were deployed to forward airfields in Afghanistan. The aircraft that had started its life monitoring Chinese nuclear tests, flying communications support missions over the same Central Asian geography, though from a very different geopolitical position. The 2017 total solar eclipse was a defining demonstration of what the aircraft makes possible. On August 21, 2017, two WB-57Fs launched from Ellington Field and flew into the eclipse path. At 50,000 feet, each aircraft remained inside the Moon's shadow for 7.5 minutes, far longer than any single ground observation site could manage. The instruments they carried included visible and near-infrared cameras observing the solar corona, and a search for hypothetical volcanoid asteroids in the dynamically stable zone between Mercury and the Sun, a search that can only be conducted during total solar eclipses and had previously been attempted only once in the near-infrared. Researchers from the Southwest Research Institute and other institutions obtained thermal images of Mercury's surface that had never been captured before. The 2017 eclipse observation was, for several specific scientific questions, the only opportunity in years. On April 8, 2024, the program executed eclipse observations again over North America with a new instrument suite, images, spectrometers, and ionosondes that were making their first airborne flights. The program's range is genuinely global. The WB-57F has operated from airfields in Europe, Asia, the Americas, and the Pacific, adapting to local logistics with what NASA describes as a minimal personnel footprint. NASA maintains its own airworthiness authority, independent of FAA certification, which allows instrument integration and aircraft modification through an internal process that saves months compared with commercial certification routes. For researchers who need to integrate novel instruments quickly, the program's in-house approach is a distinct advantage. One voice that captures why NASA maintains this specific platform rather than alternatives is direct. NASA astronaut Johnny Kim, when asked about the aircraft. Why the WB-57? Because it provides high-altitude, pressure-suited operations to NASA. The pressure suit requirement isn't an inconvenience. It's part of what makes the program unique. Above certain altitudes, the crew wears full pressure suits, breathing protocols aligned with those used by U-2 and SR-71 crews during the Cold War. The aircraft demands a level of operational rigor that few research platforms require. The people who fly it know what kind of machine they're flying. Then came January 27, 2026. At approximately 10:19 in the morning, N927NA, the aircraft that had spent 41 years in the Arizona desert before being restored, took off from Ellington Field for what appeared to be a routine proficiency flight. The crew flew for approximately an hour, performing touch-and-go landings. On the return for what was called as a final touch-and-go, the pilot transmitted "gear down" and requested clearance. Air traffic control cleared the aircraft for runway 17 right. The transmission would be the last radio call before landing. Video footage posted online showed N927NA touching down without its landing gear extended, sliding on its fuselage down runway 17R in a cascade of sparks, coming to rest on the runway surface. Emergency vehicles weren't staged, suggesting neither the crew nor air traffic control had been aware of a landing gear malfunction before touchdown. No injuries were reported. NASA spokesperson Bethany Stevens confirmed that afternoon that all crew were safe. The cause, officially described as a mechanical issue, went under investigation. The aircraft sustained significant damage and remained grounded. At the moment N927NA belly landed, it was NASA's only active WB-57F. N926NA was in a major inspection, expected to complete in February 2026. N928NA's inspection was on indefinite hold. 3 aircraft in the fleet, 0 airworthy. The Space Review headlined its analysis, "Big Wing Bird, NASA's WB-57 gets grounded." The headline carried a weight that went beyond the incident itself. With only 3 aircraft remaining from the original 21 aircraft RB-57F program, any long-term grounding of one represented a meaningful reduction in capability for a platform that NASA had described as having capabilities unparalleled by other aircraft in the government or commercial spaces. The question that aviation journalists and NASA observers immediately raised was simple. Could N927NA be repaired? And if so, how long would it take? An aircraft of this age, this complexity, this limited spare parts availability, the calculus was genuinely uncertain. April 1st, 2026, Kennedy Space Center. The Artemis II stack had been rolled out to Pad 39B on March 20th, following a full-scale rollback in February after a liquid hydrogen leak during a wet dress rehearsal and upper-stage propellant pressurization system issues that had delayed the mission into April. The crew, Wiseman, Glover, Koch, Hansen, entered quarantine in Houston in mid-March. 57 minutes before the 6:35 p.m. launch window, a NASA WB-57 departed from the shuttle landing facility at Kennedy Space Center. It climbed to approximately 45,000 feet and held position. At 6:35 p.m. Eastern, Artemis II lifted off. The WB-57's wave system tracked the ascent. High-definition imaging of the SLS stack through its first minutes of powered flight, above the cloud deck, at a resolution and stability that ground cameras can't achieve from the boundary layer. The crew of the Orion spacecraft, named Integrity, broke the human distance record from Earth during their lunar flyby, reaching 252,756 miles, breaking Apollo 13's 1970 record. The 4 astronauts became the first humans to fly beyond low Earth orbit in more than half a century. After the launch, the WB-57 landed back at Ellington. Its next scheduled flight activity, supporting NOAA's SABRE atmospheric research program, was listed for July 7, 2026. Whatever had been resolved about N927NA's repair status, a Longwing was airborne over Kennedy Space Center on April 1st. It had done what it was built and rebuilt and built again to do. The question that opened this story deserves a direct answer. What did W.E.W. Petter get right in 1944? The easy version of the answer is the wing, but that's not quite correct, because the 122-foot wing on N926NA, N927NA and N928NA isn't Petter's wing. General Dynamics designed an entirely new structure for the RB-57F program. Computer-calculated, aluminium honeycomb construction, no flaps, sealed control gaps. What General Dynamics didn't design from scratch was the aircraft around the wing. The fuselage that holds those wings, that carries 8,800 pounds of scientific instruments to 65,000 feet, that has been repaired and restored and flown by NASA for 5 decades, that fuselage traces its structural lineage directly to the airframe Petter and his small English Electric design team conceived in Lancashire in 1944 and 1945. The wing is new. The philosophy is original. The bones belong to a man who died in 1968 before he could see his aircraft photographing solar coronas or tracking astronauts to the moon. The deeper answer is the design brief that Petter accepted and executed without compromise. Build an aircraft that defends itself with altitude. Strip out everything that works against ceiling and speed. Trust the aerodynamics. Wrap the most powerful available engines in the most compact and aerodynamically clean package possible. In practice, this meant a twin-jet layout with mid-mounted straight wings in moderately clean aerodynamic configuration. No defensive armament, no excess systems, no compromises made in the name of versatility at the expense of the core mission. The brief was written for an aircraft that would be difficult to intercept. What Petter actually built was an airframe so fundamentally suited to high-altitude work, so free of the structural and aerodynamic compromises that other requirements inevitably impose, that when the Air Force needed to push a platform above 60,000 feet in the early 1960s, the most efficient solution was to rebuild Petter's airframe around new engines and a new wing, rather than start from scratch. That is the precise nature of what the 1944 designers got right. Not a specific wing geometry, not a proprietary materials choice. Not an insight that modern engineers have failed to replicate. They got right the fundamental architecture, a clean twin-jet fuselage designed around altitude and simplicity, large enough to accept substantial payload, rigid enough to support the structural loads of a dramatically extended wing, and free enough of mission-specific compromises that it could be rebuilt for missions Petter never imagined. The Canberra's longevity isn't an accident of historical preservation. It's the consequence of a design philosophy so well matched to a specific kind of work that nothing built since has found a better solution for exactly that combination of ceiling, payload, and endurance. The RAF flew the Canberra for 55 years. India flew it for 50. 15 nations operated it across 4 decades of Cold War and beyond. It appeared on both sides of the Falklands War, both sides of the Indo-Pakistani wars, both sides of multiple African conflicts. Every conventional military operator eventually retired it. 3 aircraft remain at Ellington Field. They carry pressure suits in their cockpits. Their wings droop when they're parked. The crews and researchers who work with them use a nickname that doesn't appear in NASA's official documentation, but persists in academic papers, in aviation magazines, and in conversations at Ellington. The Long Wings. The Cold War ended. Roland Beaumont, who flew VN 799 off the Wharton runway on May 13, 1949, died in 2001. W. Petter himself died in 1968. The first prototype, VN799, was scrapped. The production line has been cold for 7 decades. The Glenn L. Martin Company no longer exists as an independent manufacturer. General Dynamics has restructured and renamed itself multiple times since the Fort Worth conversion program. The 3 aircraft are still at Ellington. Subscribe for more stories like this.